Okay, chemical reactions. Chemical reaction is making or breaking bonds. So chem reaction. Make or break. If you break a bond, what happens with the energy in that bond? It's a practice question. It's released. What happens when you break the bond in ATP? Energy gets released. So the number of atoms is the same in the beginning and at the end, but the arrangement of the atoms are differently, and we'll show that. We'll show the different kinds of chemical reactions in just a second. So how do these chemical reactions take place? Make and break bonds. How do they take place? Particles are always moving around. I know we can't see them, but they're constantly moving around. And when they bump into each other, when they're in the right orientation, when they have the right speed, all that sort of stuff, when they bump into each other, they can change their orientation, so different atoms can then be bound to other atoms. And let's just get into some examples. To be able to have these collisions happen, so for example, let's say I have A plus B, and I want to make this into AB. For this to happen, you have to reach activation energy. Activation energy is a broad term that has to do with all those things we talked about, which was orientation of the molecules, enough force to actually break and make bonds, temperature, all that stuff. So this activation energy it's the energy needed for a chemical reaction to happen. To make or break bonds, you have to have a certain amount of energy put into it. Okay? So these different reactions, we're starting with this A plus B to AB. That's called a synthesis. A plus B to AB is a synthesis. If I have AB to A plus B, this is a decomposition. In our body, we mostly have these synthesis and decomp reactions, right? So we're building things up. Those are our anabolic reactions. Those are our synthesis reactions, or we're breaking things down and digestion, whatnot. Those are decomposition reactions. Okay. The other ones that we have are exchange reactions. So that's like if I did AB plus CD going to AC plus CD. This is called an exchange. That one's self-explanatory. A specific one we talk about are oxidation reduction reactions. And we'll get more into detail about those at another time. It has to do with moving electrons around. 2 phrases you can remember. If you're losing an electron, that's oxidation. If you gain an electron, that's reduction. If you gain an electron, what's going to happen to the charge? So let's say I have Na, and I've gained an electron. What happens? Well, now I have Na minus, because remember, you gain an electron, means you gain a negative charge. So I went from a neutral charge to a negative charge. So this sodium has been reduced. Leo Gurr. Okay. Synthesis, decomp, exchange. Next. This recording is a little bit longer than I like to normally go, but we're pretty close to the end, so we're going to keep rolling. Alright, next, so we did synthesis, we did decomp, we did exchange, and now we're going to look at reversible. Reversible just means that you can go from reactant to a product and then back to that reactant. And one I like to use for this is ATP. So depending on the body's needs, you can break ATP down into ADP plus an inorganic phosphate. And then you can also, let's say that you have plenty of energy, so you're gonna store it, or you don't need energy right now, so you're gonna store it as ATP. So you can take this ADP, add a phosphate, get ATP. And these are saying for adenosine triphosphate versus adenosine diphosphate. Alright, the next one, I'm going to draw a little picture for you to explain. Alright, I drew a graph for these next two. These are our last ones. This is going to be exergonic and endergonic. And endergonic. So, ergonic has to do with energy. I'm just going to do an E for energy. And then X means out. And end means in. So what this is saying is we're trying to look at what is the energy level of the products compared to reactants. Okay? If you have energy taken out of the system, then your products are going to have lower energy than your reactants. This is exergonic. So you have energy out, your products have lower energy than your reactants. You still had to put in energy. You have to put in energy to get any chemical reaction to occur. What is that called? That's your activation energy. But what we're looking at is this difference. Let me highlight it. This difference. This is what we're looking at to determine exergonic or endergonic. So now we have, once again, this difference in energy is our activation energy. But what we're looking at is the difference between our reactants and our products. So we can see that here our products have a higher energy level than our reactants. Over here, our reactants have a higher energy than our products. So this is exergonic and endergonic. It's just basically you're looking at energy levels of the reactants compared to the products. In exergonic, your products have a lower energy than your reactants. In endergonics, your products have a higher energy than the reactants. These exergonics are usually catabolic and endergonic are usually anabolic. Because if you think about this, an exergonic is going to be a catabolic reaction because we want to take energy out. So if we're breaking a bond, we know that we release energy. So this energy that's being released out is happening from breaking a bond, catabolic reaction, exergonic. Anabolic reaction, our products have more energy in them, so we can use them. Like, let's say that we're taking glucose, putting it together into glycogen. So that's going to be a storage molecule where our product, our glycogen, will have a higher energy than our reactant of glucose. So later on when we need it, we can break that bond for some energy. Okay. The last thing we're going to look at is what limits the rate of chemical reactions. We have these chemical reactions going on in the body. How can we speed them up and slow them down? What I always like to do is I like to think of how can we speed things up. I like to move in the positive direction. So one thing we can do, so these are factors that limit the rate of reaction. Okay. So what we're going to say is the factors, and instead of saying how we limit the rate, we're going to talk about how we increase the rate. So one factor is the velocity of the colliding particles. If you go back to chemistry, what is this concept called? What's another name for the velocity of a moving particle? That is also known as, different color, temperature. So if you want to increase, remember we're gonna cut that limit out and put increase. So if we want to increase our rate of reaction, we can increase our temperature. By increasing the temperature, we increase the velocity that these particles are colliding at. Next, we have energy of the colliding particles. Just put E of colliding particles. All you really need to know is that smaller particles are going to move faster. Let's think of a tube. Okay, you're at Army boot camp, and you have to crawl through this pipe. Who's going to fit through better? 125-pound Sally or 250-pound Sally? Probably 125-pound. Okay, so this is, we're saying, the smaller your molecule, let's change these into atoms, or molecules, whatever you want to say. The smaller the molecule, the faster you're going to move through this tube or colliding particle, whatever you want to say. So energy of particles, smaller particle, faster it can move. If you're moving faster, you're probably going to have more collisions. So because you have more collisions, you typically have more chemical reactions. So use smaller particles and speed them up to using high temperatures to get these chemical reactions to increase. The other thing you can do, this is my brackets, this is called concentration, okay? So concentration of colliding particles. The brackets are my abbreviation for concentration. So if you want to increase chemical reactions, then you increase the concentration of your particles. For example, this is my reaction box, and I've got some different reactants, and they're reacting with molecules B. What's going to happen more what's going to have more reactions, that box or this box? Just by looking at this, the sheer number of particles in there that are going around that have the potential to collide is so much more that you're going to have more chemical reactions or more collisions. Remember, chemical reaction is synonymous with collision. So you can increase the concentration of your colliding particles to increase the rate of a chemical reaction. The last one is a catalyst. So these decrease activation energy. They do it through a bunch of different ways. They can help orient molecules in the correct orientation towards each other for the best collision. They can... we don't have to learn that right now, so we'll stick with that one for now. They decrease activation energy. We call the catalysts in the human body, those are called enzymes. And they're not going to make a reaction occur that's not going to occur naturally. So just because you have an enzyme and you put two things together doesn't mean it's going to make this reaction occur. It has to naturally occur, but it will speed up the rate of reaction. Alright, y'all, this is a pretty long video, but that's it for this overview chapter PowerPoint.